The de Broglie hypothesis, formulated by Louis de Broglie in 1924, is a fundamental statement in quantum mechanics that proposes every particle or quantum entity with linear momentum also exhibits wave-like properties. This dual nature is a cornerstone of quantum mechanics. The hypothesis suggests that the wavelength is inversely proportional to the particle's momentum, which means that larger objects with larger momentum have shorter wavelengths, and their wave properties are not easily observable, making this phenomenon significant primarily for microscopic particles. This hypothesis was confirmed by the Davidson germer experiment, which observed the diffraction of electron waves, providing evidence for the wave-like behavior of particles. When a beam of electrons was shooted on slit-containing wall, electrons started showing interference pattern and diffraction, which is nothing but a wave property. This discovery introduced the concept of wave-particle duality in matter waves, which challenged the classical view of matter as having only particle-like properties. But this was only applicable on microscopic particles like electrons, protons, neutrons, atom molecules, etc. Or we can say only at quantum level, not on larger particles. But this does not mean that macroscopic particles does not shows wave nature. They always shows their wave nature. Electrons are just an example. But here question rises that, does our human body, this chair, this fan, and that apple have wave nature? And the answer is yes. They definitely have a wave nature, but we just can't see it. Why? See, there are many reasons to this, and one of them is quantum decoherence. Wave coherence is about how well two waves work together. When two waves are coherent, they have a constant phase difference, which allows them to interfere and can join up to make a stronger wave or cancel each other out. Their amplitude can be different. Now let's understand what is quantum decoherence. We are made up of many microscopic particles that shows wave nature. That means we are made up of several types of waves that were quantumly coherent, but while interacting with outer surrounding or environment, we lose our quantum coherency. Quantum decoherence is the loss of quantum coherence, the process in which systems' behavior changes from quantum mechanics to classical mechanics. And due to decoherency, we lost our wave nature and become particle, whose all energy is now seen as mass. But the fun fact is that even after getting recoherented, we would not be able to see our wave nature. Why? Because of very small wavelength. A normal human mass would range from 5 to 8 kilograms. That can be converted into large amount of energy, and we know wavelength is inversely proportional to energy. It can be viewed as the loss of information from system into the environment, since every system is loosely coupled with the energetic state of its surrounding. There are also some other reasons that why can't we see macroscopic particles as wave, which we'll cover in upcoming videos. So while everything is indeed made up of energy, the conditions necessary for wave-like behavior to manifest are not present at the macroscopic scale, which is why we don't see our physical bodies behaving like waves. However, researchers are exploring ways to exhibit quantum behavior in larger scale objects, like in the field of quantum optomechanics. Thanks for watching Scientific Shots. Like and subscribe to the channel and stay tuned. See you in the next video.